4C, excuse me, on motion is distinguishing between uniform and non-uniform motion and doing some simple calculations. First of all, uniform motion just means constant velocity or assumed constant velocity. Non-uniform motion means there's going to be some sort of acceleration formula. There's a few formulas we use, and I will do details with them another day, but I showed you this one earlier. Oops. This is the big one. You know, calculating acceleration. But so non-uniform motion, you're assuming there's an acceleration is the big thing. Where uniform motion, we assume constant velocity. Okay? And we'll get more into the non-uniform motion another day, not today. Again, if I go too fast, please pause. Let's just do some calculations. So the only formula you need to worry about with uniform motion is this one. Well, I guess there's two. There's the speed formula, which is distance over time, and there's the velocity formula, which is displacement over time. And sometimes those work out to be the same, and sometimes they don't. So, simple thing, what is his speed? He takes 25 seconds to travel 45 meters. There's no mention of acceleration. We assume he's traveling at constant speed the whole time. So just nice format is to write down the givens. Nice communication. D equals 45 meters. So we want to know his speed, his distance over time. So his speed is speed equals 45 divided by 25, which is some sort of meters per second. 45 divided by 25, 1.8 meters per second. Okay, so a couple things on good communication in physics. I'd like to see you write down the givens in the question, write down the formula you're going to use, put in the numbers, and then at the very end, make sure you put the units. That's important. And here's another really important one. This is more than communication. It really demonstrates understanding to me, is this, a check mark. This check mark means that number makes sense. When you're in math class, you do calculations, whatever, the numbers mean whatever they mean. In physics, that means something. And does it make sense to say that whoever Peter is, that he can travel 1.8 meters per second? And I would say that's a reasonable number. If you've got 2 million meters per second, maybe that's not a reasonable number and you don't check mark. So that check mark's important. It demonstrates to me understanding, and it demonstrates, it's also a little communication bit. So you circle and check mark your answer, that it makes sense. Okay, let's do a couple more. Now Peter is traveling, it's saying how long? How long will it take Peter to travel 250 meters if he moves at 10 meters per second? So it looks to me like we're given his speed of 10 meters per second, and we're given his distance of 250 meters, right? And we're looking for how long. That must mean time, right? So just looking at our formula, we know V equals D over T. I can rearrange that to say dt equals D over V. If you can't follow that rearranging, I'll help you in class with it. But basically, I'll just bring T to the top of both sides and then divide by V. Anyway, so this is the formula I use. And I'm going to substitute in and say T then is 250 divided by 10. Better not use a calculator for that one. It's going to take him 25 seconds. Which again, 10 meters per second, which is fairly fast. But if he's traveling 10 meters per second, it makes sense that 25 seconds would be the longer time to travel 250 meters. So that's a good answer. Another one. Let's see. He sprints at 12 meters per second, so we're given a speed. And it takes him 20 seconds. And so we want to know how far does he travel during that time period. So going back to our original formula, if I want to get D by itself, just multiply each side by T. So D equals VT. Okay? That's going pretty quick, but again, I think you can either write those down on your formula sheet, the rearranged forms, if you don't get it, or if you want further explanation, very happy to during class. Okay, so D then is 12 times 20. So that's going to be, I want to say 600, 12 times 10, it's going to be 240, 240 meters. Okay, so D. 20 seconds at 12 meters per second, that makes sense as well, so check my problem. I want to remind you again, if I go really fast, the idea is that you can always pause these videos. You don't need to keep it running the whole time. This is a big example. This one is doing a little bit of every calculation that we have so far, and I think a good way to distinguish between distance, displacement, velocity, and time. So first skateboarding to the candy store, he walks 450 meters north, which takes him that many seconds, but uh-oh, he wipes out. He stops for 30 seconds to regroup, then notices someone has dropped a toonie on the ground 30 meters behind him. So he takes 10 seconds to skate back to the toonie. And we want to find out during that time, like his elapsed time, his displacement, distance, velocity, and speed. So in a question like this, and you're going to do some of these if you choose the Hall Walk lab, which is a nice, easy lab. It's basically this situation exactly. Let's just draw out what he does. I know you're probably still copying this, but maybe pause at this point to finish copying, and then we'll do the solution. So he walks 450 north. Here's the solution. I'm going to draw it out. So we'll say, up is north. So he walks 450 north. But uh-oh, he wipes out and he stops right here. He stops for 30 seconds, and in that time he notices that back here, there's a penny, or a toonie, sorry. So he walks 450 from here to here, and he goes back minus 30 meters. So his overall from here to here will be the 420, right? That's his overall displacement, okay? So we want to know the overall time. That's easy. You just add up the time, the whole period. So for A, the entire time is 250 seconds. Plus 30 seconds to regroup when he wipes out. Plus 10 seconds to get back to where the toonie is. You add all that up and you get 290 seconds. Okay? His displacement during that time period is the difference between start and finish positions, right? So he started right here, and he ended right here. So that displacement would be 420 meters north of where he started. His distance, now that's the entire bit, that's everything he did. So his distance is 450. He went up 450, then he went down 300, so plus 30. So it is 480 meters. That's the difference between displacement and distance, right there. Then we want to find average velocity and average speed. Okay. So for D equals delta D over T. So that'll be 420 meters north over 290 seconds. And we'll say that's north. In part E, his speed is distance over time. So there you use the 480 meters.
This Ricker, please contact extension 253 for a telephone call.
About 1.7, rounding up. So when you report the V, you just say 1.7 meters per second. Okay? So that's sort of distinguishing between velocity, speed, distance, displacement. And that'll set you up nicely for your Hall Walk lab. And that's it for today's lesson.